In the previous video, we began our journey into the mathematical foundations of general relativity. In this part, we take that language further. The abstract mathematics of manifolds and tensors now begin to describe real space-time, the geometry around stars, black holes, and the universe itself. From symmetry and curvature to the geometry of black holes and the very evolution of the cosmos, this series will now move from the mathematics of GR to the physics that emerges from it, showing how every equation is in essence a story about space-time itself. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to episode 2 in learning how to understand the mathematics of general relativity. Although I have put up the first video on the I button, here is a quick recap on some of the important points that I covered in the last video. So in the last video, we actually talked a lot about this particular book, The Physical and Mathematical Foundations of the Theory of Relativity, written by Antonio Romano and Mario Mango Fernari. I divided the book, specifically the concepts, in 3 parts. The first, we start with the concept and mathematical foundation. Second, the current video's topic, the formal mathematical exposition. And third, we will look in the geometric evolution in this series of videos. So these are the things that we covered: tensor algebra, differential manifolds, calculus, special relativity, continuous systems, introduction to GR, and Cauchy problems in Einstein field equations, followed by Schwarzschild black holes and cosmology. What we covered, some important points are this. We started with the concept of what is called the optical isotropy principle, which Newton thought that light could have different velocities depending on the medium or direction, but Einstein showed us that it is same in all inertial frames of reference, which led to what is called the Minkowski metric. We also encountered a very important thing which is called the Cauchy problem in Einstein field equations, where the general Newton's law of a simple ordinary differential equation won't be that easy to solve. So in the Cauchy problem of general relativity, we try to find out, if you know the initial conditions, how will the future evolution of the entire space-time geometry will work out. We also looked into what is called the absolute differential calculus, which is now called in modern language the tensor calculus, the need for covariant derivative Christoffel symbols, and Riemann curvature tensor. And finally, I reviewed the strengths and the weaknesses of the book, which led to a comprehensive understanding of the first book and our first step in the mathematical journey, building up the foundation from both physics and mathematics. Now we move from the basic foundation that we laid out in that book in the formal mathematics of GR. So here you can see that we covered primarily about the foundation and philosophy, the approach that built from mathematics, physics, and relativity, and the reader's experience was more or less conceptual, reflective, physically grounded. So it began actually with tensor algebra, the book. Then the authors actually talked a lot about Newtonian mechanics, revisiting the Newtonian mechanics, finally general relativity, and emphasizing why geometry explains gravity. So what was thought to be a general force, a fictitious force, what we saw that the reality was made up of objects in space and forces acting between them, and that geometry actually became the underpinning force of the reality. Now, we come to the part of our video and understanding that we can ask this question. We saw that geometry becomes reality. Now the question is that how far can this mathematical structure go? Or we can say, where did this kind of geometry actually comes from the first place? And in order to do that, we are going to take ahead with the second book in our journey of general relativity, which is called General Theory of Relativity, a Mathematical Exposition, written by Onadijibon Das and Andrew de Benedictis. Well, if you talk of the book, this is the cover of the book. It is from the Springer. And again, I could not find a lot about those two authors. No photographs, etc. I found a little bit about from their Google Scholar. I put it up here. But I found a more or less picture, a photograph of Onadijibon Das. But I was not very sure that he is that mathematician, so I have ignored that. Now, in this book, there are a few things which the authors have mentioned right at the beginning. it tells that this book is well suited for advanced mathematics or physics students. So it is not for a beginner. Second, it tells it covers all the important subjects in this field of classical general relativity in a mathematically precise way. Again, emphasis on mathematics. The second part tells that we have therefore provided extensive discussions and proofs to many statements, which seems surprising at first glance. Now then the authors tell that there are also many elegant results from theorems which are applicable to relativity, and in doing those we hope that the final result is reader friendly. So a lot of points are being made. I have just highlighted few of them so that you can basically understand whom it was meant to, what are the mathematical prerequisites that you need to have. So from there I have just summarized that here gravity is explained as the curvature of space-time, not a force. The audience is basically written for advanced students and researchers. The approach is a kind of a balancing between rigorous mathematics and the physical intuition. The clarity is clear, efficiency includes elegant theorems, and the tone is basically strikes a middle ground between the brute computation and the elegance of Einstein's field equation. The goal is basically to cover the key topics based on mathematically precise yet in an approachable way. So we can take it from here that we are going to venture a truly mathematically advanced book in understanding the deep-rooted part of general relativity. But don't worry, I have made the mathematics and the basic understanding a little bit clear. The first part of the book actually starts with this, which is not very different from the first book of Romano, Tensor Analysis on Differentiable Manifolds. So as we know that Einstein field equations heavily depends on tensors, so we need tensors because they are much more powerful tools than vectors. So it is the same thing which I have taken from my previous understanding, that if you are walking around a surface which looks global, it would actually be local, or seems to be Euclidean. It is a kind of a flat Euclidean space when you consider the local part. So that which locally resembles Euclidean space near each point is basically called a manifold. Manifold was originally coined by this great mathematician Bernhard Riemann. I've made many videos in differential geometry courses where you can find the entire history, the Göttingen famous lecture where he first coined the term manifold. So from here what we can find, if we take this kind of a differential manifold where it is a positive, negative and zero curvature, and these white boxes are pointing that these are isomorphic, or we would say technically homeomorphic to a Euclidean space. So differential manifold is a way, it is a simple way where you can use calculus, because in general theory of relativity we are actually dealing not with flat space but with curved space. These should be smooth so that you can apply calculus. So that is what the book actually starts with. So here you can see the content of the book. Up to 88 pages are basically on tensor analysis on differential manifold. The chapter introduces manifold, tensors, and you can learn how they describe on a higher dimensional space. So this is actually here what the book tells about, that general relativity describes gravity not as a force but as a geometry, and once you start applying calculus you can actually measure, differentiate things on a curved surface, and you can say that you would actually start learning the grammar before reading the poetry. Now, apart from this entire 86 pages which I have gone through in the first part of differentiable manifold, one thing came very striking, very important and very lucidly explained, and that is what is called the concept of a parallel transport. Now, if you look closely at this figure, what you can see is that it shows a vector v which is moving around a closed path on a curved surface which is called a manifold. And the parallel transport actually means you move the vector step by step without rotating relative to the surface. And when you return, which is given by this delta v kind of a structure, you return to the starting point, the vector's direction changes, which is represented by delta v. And this actually is the changes due to, not due to rotation in space but due to the curvature in the manifold itself. So a non-zero change, as I have mentioned, after a full loop means that the space is curved. So here now you can see this book gives a wonderful visual I would say, a real world visualization. So the first part shows that the vectors transported around the loop return exactly as they started. There is no change. That means the surface is flat. There is no change. The second part, as it shows, the cylinder is flat intrinsically. You can unroll it into a plane. That means again parallel transport around the loop of the cylinder gives no net change in direction. And typically the cone is very interesting because it is locally flat everywhere except at the tip, that is at the apex. So when a vector is parallelly transported around the tip, it does not come back aligned. It rotates by a finite angle. So this shows that curvature can be concentrated at a single point, the apex. The key line, I would say, or the key takeaway from this is that non-trivial parallel transport may be obtained even though the entire curvature lies in flat regions. And that is basically a wonderful exposition given through cone. So this is something which I think is very, very important. So what this parallel transport part it tells conceptually here, you can see that around here what it tells that curvature is something intrinsic. I have kept the geodesic movement along it. So it is not about how the surface bends, but about how vectors they loop around when they are transported. The failure of a vector to return to its original direction actually measures the curvature of the space. And general relativity is basically this space-time curvature. So here what we can say that if a geodesic or a free fall, here you can see the image of a free fall path, follows actually a parallel transport of its velocity vector. It is moving around, that means we are transporting, isn't it? This person, if I consider this to be a free fall, you can consider this person to be this blue dot, which is circling around this red mass. So if you move around a closed path in a space-time and see a change, that is the effect of gravitational curvature. So you can have regions that are locally flat like the cone surface, which we have seen, but still have global curvature due to the topological defects or singularities, which is similar to mass concentration in space-time. So this is very important to note that when we are making a free fall, the parallel transports of its velocity vector. So if you move around a closed path and in space-time and you notice a change, then that is the effect of the gravitational curvature. So that actually covers the first part of the video of the video and the book, and parallel transport is extremely important. The next part of the book talks about what is called a pseudo Riemannian space-time manifold M4. Now I will go in the book later, but first let me explain what is meant by a pseudo Riemannian manifold. Now you have already noticed earlier that you already have a kind of a smooth differentiable manifold, for example M, and these are different collection of points that actually, so a smooth differential manifold M which has got points, a collection of points, the orange points that locally looks like R4, and it also allows differentiation. We know that. So this is basically definition of a manifold. You have a smooth manifold M, a collection of points that locally looks like R4, and it allows differentiation. But that is just the stage. It tells how to move and differentiate, not to measure anything. Now say for example, if I put something like here, if I want to measure distances, angles, curvatures, then what we need, right? What we need is basically an additional object, and that additional object is called a metric tensor. I will come to metric tensor later because it is a huge part in general relativity. Remember that once we want to measure something, if you want to measure these things, I mean to say this triangle or something like that, we include a metric tensor, and including metric tensor actually lets us move from topology, I would say pure topology, to geometry. So we can say from here that a Riemannian manifold is basically a differentiable manifold just like that, but it has got a tensor component M, G. And it is equipped with a positive definite metric tensor, which is GIG. Positive means that this would be greater than 0. So from here what we can say that if I square the length of any non-zero vector, it is always positive. Obviously negative, square, whatever it comes, it is positive. So there are no directions that can actually give a 0 or a negative length. That is terribly important. So that means if I take this kind of a manifold, all those areas which are moving this way, this way, this way, or that way, it is always positive definite. That means there is no distinction between space and time. All directions have positive length, whichever the way we are going. So this is basically what is called a Riemannian manifold, smooth differential manifold. In order to measure, we put a metric tensor, and from there we get a Riemannian manifold. Now we come to the basic question, what is a pseudo Riemannian manifold? So pseudo Riemannian manifold is also a differential manifold which also have a metric tensor G, but the metric is not positive definite. That means it has mixed signs, both plus and minus. So for a 4-dimensional space-time, we have this kind of a metric. So here, because G, V can be positive, 0 or negative, we get 3 kind of class directions, which you already know. And this is time-like, space-like, and null-like. So all these taken together actually gives a distinction that, between its causal structure and what can influence. So why we call it pseudo? Because it comes from the Greek word which means almost. I won't say fall, but almost. It means almost Riemannian, but not quite. So it is called pseudo because it almost has the structure of a Riemannian manifold, which you can see from here. This was the definition of a Riemannian manifold along with a metric tensor G. But only thing is that it has not only got a positive but the metric of indefinite signature instead of purely positive. That means it can have a negative signature, which I have shown you here in -1. I will show you further. Now if you look at the space-time Minkowski metric, which looks like this, and if I take the natural unit c equals to 1, we get this. So corresponding matrix is this one. So here, if I take the time component G00, that one negative sign in the time component G00 -1 actually means that the metric is indefinite. So that one negative sign in the time component means the metric is indefinite. So that means it can produce both positive and negative values, and hence it is called pseudo. So remember that it is still asymmetric, non-degenerate bilinear, but it is not positive definite. It has both positive and negative directions. So in Riemannian geometry, length is always spatial, no distinction between backward and forward movement, no causality. But in pseudo Riemannian manifold, the metric allows for a negative sign which distinguishes from the time, prime and space. So positive definite metric describes geometry, and the indefinite or the pseudo metric actually describes the reality. And the second part of the book actually talks about this, the pseudo Riemannian manifold. So we learned the manifold first, then we learned what is called the tensor analysis on the manifold. We saw what is basically free fall and parallel transport. Now we are learning what is called a pseudo Riemannian manifold. Now from here, these things seem to be complicated, and to make things a little bit easier, the author moves in a very important chapter which is called spherically symmetric space-time domains. What do we mean by that? Now because spherical symmetry lets us solve Einstein field equations easily, so the equations are, as you understand, the equations are extremely non-linear, and they are very complicated, and you know, we can find closed from metric that describes no physical situations. So mathematically we can tell that a space-time is spherically symmetric if its matrix measures this one, right? Okay, let me show you some interesting thing. This is bilaterally symmetric, this is radially symmetric, and this is spherically symmetric. Now this is again non-spherically symmetric because we got a division in between, but this is again spherically symmetric. So spherically symmetric means if its metric remains unchanged under any rotation of the two spheres, technically speaking. Now why we are learning spherically symmetric spacetime dimensions? The reason for this is that spherically symmetric solution describes and makes the equations much more easier. We don't have to include rotation, don't include charge or anything. So these are ideal conditions which helps us to solve Einstein's field equations much more easily. So here you can see, because the gravitational field of stars, planets, black holes, almost every astrophysical applications of general relativity begins from here. And it actually teaches you how to connect mathematical curvature to measurable quantities like gravitational redshift, time dilation, escape velocity. Right on the screen, what you see is basically the Schwarzschild solution, and this is also spherically symmetric, non-rotating, uncharged. So if it was not spherically symmetric, if it was rotating, if it carried a mass, things would have been ideally very difficult. So that is why we are studying what is called spherically symmetric space-time domains, and Schwarzschild solution, etc. in this part of the book actually explains that. So that is why we need spherically symmetric understanding to solve Einstein field equations easily. The next part of the book talks about what is called static and stationary space-time domains. Now this chapter is also closely related. This is the content of the chapter. Now this chapter actually relates to family of symmetry of space-time, time independent. There is no rotation. Again, these are for making life easy, and the metric components depend only on spatial coordinates. For example, Schwarzschild space-time, non-rotating mass. So why we are learning this? We are learning this because almost all real astrophysical objects, stars, planets, etc., they rotate, and spherically symmetric is an idealization, and as you can see right now within a few minutes time, that it actually prepares you for the Kerr black hole or the Kerr geometry, which is fundamental and which is rotating. So just remember here that still time depends but may involve rotation. Metric components are constant in time but include cross terms, and this is an example of Kerr spacetime. So the chapter actually generalizes from the perfectly, I would say, spherical and static to axially symmetric and rotating geometries. Now here is a quick note which I have put it over here. As you can see, it comes zooming, that a space-time is said to be axially symmetric if it looks exactly the same when rotated around a fixed axis. It does not mean rotation in motion. It means that when it is rotated around a fixed axis. So because almost all astrophysical objects rotate, so this chapter actually teaches you rotation, twist, space-time, frame dragging, ergosphere, and so on. And if I talk of this particular part, this is extremely important, the general stationary field equations. Here we will be rewriting the Einstein field equations in the static axially symmetric case. So just, the book is so beautifully written, it is taking the step by step. First it talked about spherically symmetric, then it is taking a little bit of rotation. And here the general stationary field equations will be written in static but axially symmetric case. And what is axially symmetric? It is axially symmetric if it is rotated around a fixed axis. Then the book comes into the general part, black holes and cosmology. This is the content of the book. So here we learn first about Schwarzschild symmetric black holes. Then we go for the Kerr black holes. As I told you, you can see Kerr black holes, page number 384. So because it includes space-time, drags, rotation, etc. Then it goes in exotic black holes, explores extension and generalization, and we can say that from the calm symmetry of the Schwarzschild metric, which is non-rotating, non-charged and spherically symmetric, we actually move into the Kerr space. So it shows how Einstein geometry folds in on itself, creating horizons that even light cannot cross, that is the black holes. Now from here, the author takes another big leap into in a very, very important concept, which is called algebraic classification of field equations and the coupled, we called it EMKG, or the Einstein-Maxwell-Klein-Gordon equation. Now what is that and why the author is doing so? Let us understand. Now this is the content of the book. Now you will see here, I will first try to explain this part, algebraic classification based on Petrov classification. Now you can see this is basically a kind of a table. This is just a kind of a table. Now what it tells about this table is that instead of going from coordinate to coordinate, Petrov classification tells that what kind of gravitational field you are looking. Type 1 is general, type 2 includes some radiation, type D Schwarzschild Kerr, type 3 certain pure radiation, and so on. So that means you are looking at static, rotating, radiative just from the algebraic structure of curvature itself. So the advantage, you will say, so why we are classifying those curvature tensors in different ways? Obviously there is a reason, and the reason is that it is purely geometric and invariant, and that is the target of physics. And it does not label, it depends on the labeling of the points, as I told you. So even if you have two metrics look completely different in equations, if they belong to the same Petrov type, they have the same underlying curvature structure. You can talk of a kind of a grouping or a kind of a topology where we group things under certain classes. So this is extremely powerful because it is like discovering that how materials are made up of the same crystal lattice despite they have different appearances. So Petrov classification, the table that you are seeing right on the screen, actually tells you at a glance whether you're dealing with a static field, a rotating mass, or a propagating wave. So algebraic classification, why it is important, that means it is just studying the structure. It is geometrically invariant and it is not depending on the label points. From here, the authors take us to what is called the coupled Einstein-Maxwell-Klein-Gordon equation. Now, this is actually a classic. This is actually wonderful. Now, why is that? Because if you see that the interaction of Einstein's field equation along with Maxwell's electromagnetism and scalar fields are actually basically going towards the theory of unification. So they represent the most complete and unifying systems in what is called classical field theory. So that means taking gravity, electromagnetism and matter field, we are trying to find out a single self-consistent geometric framework. A single self-consistent geometric framework. So from here, if you can further take another table, you can see how beautifully it is arranged. So general relativity by itself only describes space-time and gravity, isn't it? It is nothing about light or matter. So adding Maxwell and Klein-Gordon equations, you actually can see in the table, you bring in electromagnetic fields, you bring in scalar fields. So this system represents a unified classical field theory. So geometry equals to space-time curvature, field is equals to electromagnetism, and matter equals to scalar field. So we can say that the Klein-Gordon equation is the relativistic wave equation, obviously for a spin zero quantum particle, and by coupling to it, it is actually establishing the classical limit of many quantum gravity models. So that means it is basically taking a step towards coupling with Einstein's matter, with Maxwell's electromagnetism, and with the Klein-Gordon equation, which is of the scalar field. It is trying to get together and find out a theory of everything, or a unified theory. So that is why you can see in this part of the book, we started first classifying the curvature based on Petrov classification, and then when we went into the coupled Einstein-Maxwell and Klein-Gordon equation. So that itself completes the total content and a step-by-step understanding of today's video. But however, I would like to give a quick critical review of this book of Anadi Jiban Das and Andrew de Benedictis. Now, if I start with the strengths, it is all great because it is beautifully arranged, and the language starts logically from curvature tensor analysis. It bridges the gap between geometry to physical reality. It contains a huge depth and coverage because it doesn't stop only on Einstein field equation. It takes to Newman-Penrose formalism and then to EMKG, a coupled system. So the coverage is quite great, and also that it has got a very organized hierarchy. So it will start with differential manifold, then go to curvature, then go to symmetric solutions, it's a static symmetric solution, then black holes, cosmology, and field couplings. If I talk of the weaknesses, only thing that I would say that it is very, very heavy in mathematical rigor, and you need to have a very good understanding of tensor calculus and differential geometry. Also, what I found that the book doesn't contain much of a diagram which would make even intuitive people like me understand physics or mathematics better, but it is missing in this book. So what is, in my opinion, about this book of General Relativity, a mathematical exposition? Well, what I would say is that if you're really, really deeply interested and you have a kind of a knack towards deciphering and understanding big integrals and big differentiations and differential geometry taking up to an advanced level, definitely it is one of the best book. What I found it. You cannot be a beginner to start this book. I would appreciate that you should have at least a researcher level or a graduate level or postgraduate level understanding of mathematics, and it actually gives a unified vision of gravity as geometry. So that's all for today's video. If you have liked it, please do not forget to subscribe to my channel Physics for Students and click on the bell icon so that you get all the notification from Physics for Students. You can follow me on my Facebook and other social media handles, and you can write to me at this email ID, which I try to respond as early as possible. We have couple of videos left in this series, but do not worry, because Physics for Students will be back with producing more interesting and fun learning videos on physics and mathematics. See you soon in the next video, but till then, may the good Lord be with you.